In this video, I'm going to talk about architectural design patterns. Patterns are a means of representing, sharing, and reusing knowledge. It's a stylized description of good design practice which has been tried and tested in different environments. The pattern should include information about when they aren't useful, and they could have tabular and graphical descriptions. So in this video, I'm going to look at some of the common architectural patterns that exist. We're going to look at a brief example of each one, and just note that these are some of the more common ones, and you should limit yourself to just these because there are others out there. So I'm going to start off with the MVC pattern. MVC separates the presentation interaction from system data. You have three logical components that interact with one another. The model component manages the system data and the associated operations on that data. The view component defines and manages how the data is presented to the user, and the controller component manages user interaction and passes these interactions to the view and model. So I'm going to take you through the example, and then we'll summarize a bit more. So this is it in a broad sense. You have the three different parts, which is the controller, the view, and the model. Controller, that maps user actions to model updates and selects the view. The view renders the model and requests models update and sends the user events to the controller. And the model encapsulates application state and notifies view of state changes. So here's the example of a web application using this model. So the controller in this case is does two things, which is the HTTP request processing. It also does application specific logic, and three things, and lastly it does data validation. The view section, it talks about how you dynamically generate pages and how you manage the forms. The model is the business logic and the database, and this is the kind of interaction between the different between these different layers. You try to use the MVC pattern when there are multiple ways to view and interact with the data. So in the case of a web browser, obviously, when we're dealing with a lot of web data, there are a lot of different ways you can present and interact with the data. You also use it when the future requirements for interaction and presentation of the data are unknown. The advantages are it allows the data to change independently of its representation and vice versa. It supports the presentation of the same data in different ways with changes made to one representation shown in all of them. However, the disadvantages of this is that it can involve additional code and code complexity when the data models and interactions are simple. The next pattern that you're going to come across is layered architecture, which is used to model the interfacing of subsystems. It organizes system into a set of layers or abstract machines, each of which provide a set of services. It supports the incremental development of subsystems in different layers. When the layer interface changes, only the adjacent layer is affected. However, it is usually artificial to structure systems in this way. So we're going to go through an example in a sec on sharing copyright documents. Here's a generic layered architecture. So you see on top layer you have the user interface, and then below that you have the user interface management, the authentication and authorization. Then you have the core business logic, applications functionality, and system utilities, and system support at the lowest layer. So that's it presented generically. So how we can modify this for a library system. So you see on the top we have the user interface, which is the web browser interface. Then the layer below that we're talking about the login, the query manager, the print manager. Then layer below that you have distributed search, maybe document retrieval, rights administration, and some kind of accounting. And then below that you have a library index, and then at the bottom layer you have the actual specific databases with the information in the system. So that's how you can apply the layered architecture. So You usually want to use this when you're building new facilities on top of existing systems. When the development is spread across several teams with each team responsibility for a different layer of functionality. When there's a requirement for, say, multi-level security as well. The advantages is that it allows replacement of entire layers so long as the interface is maintained. Redundant facilities can be provided in each layer to increase the dependability of the system. Uh, in practice, however, providing a clean separation between layers is often difficult, and a high-level layer may have to interact directly with lower-level layers rather than through the layer immediately below it. Performance can be a problem because of multiple layers of interpretation of a service request as is processed at each layer. So, say a popular place that this layer architecture is used is in data comms, for example, like say the OSI model, or any kind of stack-based type thing, like on routers in data comms when they have to routing from one place to the other. Usually, you have very specific hardware, like in routers, such as CAM memories and these kinds of things, that allow you to do quick lookups and that kind of thing to overcome the disadvantage of the interpretation of the different layer levels. But that's getting into, say, a whole bunch of hardware specifics. Okay, so that gets me into the next architecture, which is known as repository, and it's all about subsystems that are exchanging data. And you can do that in two ways. Either you have a shared data repository where it's a central database and everybody's going to access that one shared database, or each subsystem has its own database and passes data explicitly to other subsystems. In a lot of practice scenarios, it's not usually neatly one or the other. A lot of the times you have hybrid approaches between shared and distributed data repository techniques, which of course brings a whole host of issues like, say, data concurrency and that kind of thing, data synchronization, some of these other kind of issues into play. You kind of use that when large amounts of data to be shared. The model for sharing is most commonly used, as this is usually pretty efficient. But of course, there will be issues that will crop up, like, say, locking data, using semaphores so that you don't interact. So when you have multiple processes interacting and that kind of thing. So we're going to see now an example of this. So you see here we have a IDE that you're going to make. You have the project repository at the center. You have a whole bunch of different editors, design translators, code generators, analyzers that are going to access all the projects in that repository. In general, use the repository pattern when you have a system in which you have larger volumes of information generated and have to be stored for a long time. You also use it in data-driven systems where the inclusion of data in the repository triggers, say, an action or two. So that's what you call implicit interaction. The advantage of this is that components can be independent. They don't need to know the existence of other components. Changes made by one component can be propagated to all components. All data can be managed consistently. As well, that's because it's all in one place. The disadvantage of this is that the repository is a single point of failure. So problems in the repository can affect the whole system. You can become inefficient in organizing all the communication through the repository because you're going to have a lot of interfaces just tapping into it. And distributing the repository across several computers may be difficult, and it brings its own host of problems into play. Okay. The next pattern is the client-server type architecture. The distributed system model, which shows how data and processing is distributed across a range of components. You can, of course, implement this on a single computer. You could have a set of standalone servers which provide specific services such as printing, data management, and that kind of thing. a set of clients which call on those services, and then you have to have a network that allows the clients to access the servers. um, so you could have something like, say, a film and video DVD library. So um, here we have the example. The communications backbone here is the internet. We have multiple clients all accessing through the internet, um, a whole set of different films and that kind of thing. So basically, Netflix in a nutshell is a good example of a client-server architecture. You use this when data is in a shared database and has to be accessed from a range of locations. Because these servers can be replicated, um, it may also be used when the load on a system is variable. The principal advantage of this model is that servers can be distributed across a network. The general functionality can be available to all clients and does not need to be implemented by all services. However, each service is a single point of failure, so is susceptible to denial of service attacks or server failure. Performance in these cases may be unpredictable. That's because it depends on the network as well as the system. So think of when the internet is really terrible, streaming movies can be a pain. Maybe management problems if servers are owned by different organizations. Okay. This is the last pattern that I'll cover in this video, which is the pipe and filter architecture. Pipe and filter is all about functional transformation processes that, which process the inputs to produce outputs. An example of this is what you do on a Unix shell prompt. There are many variants of this approach. When transformations are sequential, this is a batch sequential model which is used in a lot of data processing systems. It's not really suitable for interactive systems. This is a very transformational type model. The example you see here is some invoice payments. The invoice and payments are inputs to this system. Invoices go into read the issued invoices, then you're going to transform that by identifying the payments, and then you could issue receipts, and then receipts comes out the end on that first thread, or you could find the payments that are due, issue payment reminders, and reminders come out on the other end. So you see the data is successively just processed by different processing agents, and it's transformed as it goes through the pipe and filters. So the pipe is the flow of the data, and the filter each one of the things that is going to transform the data from one stage to the next. You use this in data processing application, both batch and transaction based, where inputs are processed in separate stages to generate related outputs. The advantage is that it's easy to understand and it supports transformation reuse. Workflow style such as this, it matches the structure of many business processes. Evolution by adding transformations is straightforward. You can implement this as either sequential or concurrent systems. The disadvantage is that the format for data transfer has to be agreed upon between communicating mechanisms. Between communicating transformations. Each transformation must pass its input and unpass its outputs into the agreed form. This increases the system overhead and may mean that it's impossible to reuse functional transformations that use incompatible data structures. So that brings me to the end of this particular video. Thanks for watching.